So today we're going to be taking another step to look at nuclear stuff. We're going to be focusing a lot on nuclear medicine today. This is going to be the first of a series of lectures dealing with what we're going to call nuclear reactions. These are not the natural reactions we've been looking at, the decay equations, but these are human-created nuclear reactions. I want to start by making sure you have a summary of all the different particles that you're responsible for knowing when you write nuclear reactions. So we have alpha, beta negative, and beta positive. The symbol, alpha, beta negative, beta positive. And then what the particles actually are. So when you write your equations, it should be 4,2 helium, that's for your alpha. Your beta negative is 0, -1 electron. And your positron is 0, 1 E. Remember, the number up top is the number of protons plus neutrons. So we don't have any with our betas. And the number on the bottom is the charge of your particle. +2, -1, +1. Remember that alpha particles are emitted from large unstable nuclei. Beta negative are electrons emitted not from the electron shells, but from the nucleus itself, as a neutron turns into a proton. The positron is very similar. It comes from the nucleus, and it happens when a proton turns into a neutron. Finally, we have our gamma. Our gamma, which is just light, so it's going to be 0, 0 gamma. And it is high energy light emitted to take energy away from a nucleus. All right, so pause if you didn't get this all done. Then we've got 3 more particles that we've barely used. A neutrino, that's the Greek letter nu. Kind of fits for neutrino. It kind of looks like a V with a little bit of a curve to it. 0, 0. Again, it has no mass, no charge. And it carries away nuclear spin. So when a proton turns to a neutron, the up quark flips to a down quark or vice versa. That spin that is lost is carried away by the neutrino. We have protons and neutrons. Sometimes they will appear in our nuclear reaction. Proton is just P, neutron is just N. A proton is actually a hydrogen atom without the electron. So we can write it as 1 proton with a charge of 1, H, because it's hydrogen. A neutron has no charge, but 1 particle that we call nucleon, a proton or neutron. In this case, it's a neutron. Again, the neutrino carries away spin. This is a single proton without an orbiting electron. So it's not actually an atom, it's just a nucleus with just 1 proton. And this is just a loose neutron. All right? So again, pause if you don't have this chart completed. Make sure you know all these particles and can use them when you need to. This is the most important column because that's how we're going to write them in an equation. Okay, so I want to remind you that what we've done so far is natural radioactive decay. We have a plutonium-210. It's sitting there, and at some random time, it gives off an alpha particle. We can't predict when it's going to happen, but we do know when it happens, it will turn into another isotope, and the alpha particle will shoot out into space, and the energy is caused by the loss of mass for the system. We know that there are many isotopes which are 100% stable, and we know that some isotopes have long half-lives and others have short half-lives. What we want to do today is make our own isotopes. This was first done by Marie Curie's daughter. Her name again was Irene Curie. She was part of the team that did this. She won the Nobel Prize for this discovery. And again, you could see her years. We have human controlled transmutation of elements, 1934. What this means is we didn't wait for elements to decay on their own. We took stable isotopes and we made them change into something else. Human-induced changing of the elements. And this is one of many that she actually was able to pull off in her lifetime. So she started with aluminum 27, which is totally stable, but she bombarded it with alpha particles. Again, not the atoms, but just the nucleuses. So we have to strip away all the electrons. We have to add particles to the nucleus of aluminum. And what happened is we got a much bigger isotope and one neutron that shot off. So use your ideas of nuclear reactions that we've already used to figure out what she produced. So make sure the charge on the left equals the total charge on the right. Make sure the nucleon numbers add up on the left to what they add up to on the right. So take a minute to do that and predict the new isotope that Irene Curie was able to develop. Hopefully, you got phosphorus 30. You'll notice that this phosphorus 30 is unstable and it will beta positive decay with a half-life of about 2.5 minutes. So she was able to create from a stable isotope an unstable isotope, which would then beta positive decay into something else. Well, it turns out that this process of making an unstable isotope with a really short half-life will become incredibly important. And it's used predominantly in the medical field. When we need to treat someone with nuclear medicine, we want to treat them with isotopes that we can create on the spot that will have a really short half-life. We want to get that radioactivity into the body to do its job and then have it decay down to a safe level really quick. So human-created isotopes, which we could then use for some practical purposes. Okay, I want you to realize that the phosphorus 30 was not on your isotope sheet. That's okay. Your isotope sheet is incomplete. I can't give you every isotope ever discovered by humans. And I just wanted to show you, these are all the isotopes just of phosphorus to show you just how crazy it is. You'll notice there's only one stable one. All the rest are unstable. So just remember, the isotope sheet I gave you is totally incomplete. It only has a few elements and then only a few isotopes of each of those. Okay, you don't have to write these down, but I want to show you some of the top isotopes that are used in nuclear medicine. I do want you to write down the two categories that these isotopes fall into. So you'll see that many of them are used for what we call imaging, and some of them are used for what we call therapy. Imaging means we give the person the isotope. That isotope then collects in soft tissue or an organ in the body, and then as it decays, we're able to use imaging techniques to see exactly what's going on in that soft tissue or in that organ. We can't use things like an X-ray because X-rays just go right through the soft tissue. So X-rays are great for looking at bones and things like that, but oftentimes to be able to image different organs or soft tissue in the body, we give the person an isotope. Depending on what part of the body we're going to be imaging, determines which isotope we're going to give them. Iodine, for instance, collects really well in the thyroid. So if you're trying to image the thyroid, you'd be giving your patient the iodine 123 and allowing it to collect in the thyroid, and then viewing it through some sort of imaging technique and see how well the thyroid is taking up the iodine. Therapy, on the other hand, means we're actually using the isotope to actually try to cure something in the body. Maybe it's trying to kill cancer cells. This is a pretty tricky technique. We need to get the radioactive material right where we need it, and we want to destroy the bad cells without damaging the good cells. So again, usually we want these half-lives to be pretty short so that they go in there, they do their job, and then they're gone from the body pretty quickly. The problem is the half-lives are sometimes so short that you need to be able to create that isotope on demand. You can't create it a week ahead of time and ship it through Amazon or the US Postal Service, because by the time it arrives, it's no longer going to be active. All right? So we want to create these isotopes. We want them to be short-lived. We want to create the correct isotope for the different job that we're trying to do.